and here we go. We have liftoff. Propulsion continues to be nominal.
RCPA chamber pressure looks good.
Following up.
Water towers, fly! Yes!
Tango down to nominal.
Flight downside at speed off. Bring in at speed off. It's orange!
Orange 45. Oh my god! Oh my god!
Decollage. What is it? Put that in the big bag, Segal.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
This methane will be igniting in the flare, correct?
Yikes. You good? Sure. We don't need any more of these.
Drill, let me know if you can see me. John Galloway with NSF. You might know me as DOS. You should be able to hear me as well. Unless you could read lips, you might not know what I was just saying if that part's not working. But give me some 5x5s in the chat over there to let me know that you have acquired our signal for today's Intrepid Museum Astro Live. You know what we do. We do the shows here once a month with Intrepid Museum, and we get cool folks who have cool stuff to talk about. We get scientists, engineers from NASA, from all over. Today, we're going to be talking about NASA's Dragonfly mission. Now, what's Dragonfly? You think of something that flies, like a little quadcopter, droney sort of thing, and it's like, oh, a little cute drone that I can fly, right? And hold it in my hand and it zooms around or whatever. Maybe you wear a VR goggles and do whatever, right? Well, Dragonfly is not a drone. Don't call it a drone. It doesn't like that. It is actually an octorotor. Octocopter? It's got 8 rotors on it, and it's almost as large as a vehicle, like a car. I don't know if it's like a European or an American-sized car or whatever. Somebody in chat's going to have a truck and be like, it's not as big as my truck. I could put it in the bed of the truck. Whatever. It's pretty big, right? And so today we are going to talk with 2 folks from the Dragonfly team about what the mission is, where it's going, and what it's looking for as it heads out on its mission. I mean, it's one of those things, right? You think that like a nuclear-powered flying robot exploring an alien moon sounds like science fiction, but then you talk to these folks and you realize that this passed peer review and got funded. And they're going to do it. So, for now, I think we are good to go. I see plenty of 5x5s in chat. Quick housekeeping. If you've got questions for us, this is a live interactive show right now. Tag us if you've got questions at NASA Spaceflight, at NSF if you're on the NSF channel. If you're on the other channels, if you're on Intrepid's Facebook or Intrepid's YouTube, wherever you are, just ask your questions and we'll try to get some of them here in front of the experts who are the best folks to answer them. Also, remember, these shows don't just magically happen. There's not like a make show button happen, although sometimes Kevin acts that way. He is very good at making the shows happen. But Astro Live is supported through a NASA cooperative agreement awarded to the New York Space Grant Consortium. Also, down at the bottom, you'll see that you can help Intrepid keep these types of shows going with the fundraiser for keeping Intrepid's educational program. So, we don't make the show about that, but if you do that, we really do appreciate it because we can keep bringing you cool, interesting content. Now, it's not just me, as I have alluded to. I'm going to have help today. Let's kick it off with Elysia Segal from Intrepid Museum. Elysia, how you doing today?
Hi, everyone. I'm doing great today. Getting a little cold outside, had some snow last night, but very excited to be here. I am super excited about this topic. If you have been a longtime viewer of our show, you might remember that back in March of last year, it was a long time ago, we talked to Travis Brown, who is the chief engineer of the Mars Ingenuity helicopter,
right.
Essentially about the entire lifespan of that thing from start to finish. It was kind of an emotional journey, actually. And he kind of teased to us at the end that they were working on something new, this octocopter idea, which blew our minds at the time, of course, and it seemed like something out of science fiction. But here we are today, now actually talking about this amazing Dragonfly mission. This month on Astro Live, we are once again teaming up with the amazing folks at Johns Hopkins University's Applied Physics Lab to talk about the upcoming Dragonfly mission to Titan, which is Saturn's largest moon. I got my Saturn earrings on here representing.
Nice, of course you do.
But it really is a really interesting place to talk about and explore because like Earth, it's got this thick atmosphere, this organic chemistry, but unlike Earth, it's got rivers and lakes made out of methane. So not the most habitable environment for us, as humans. But those conditions potentially might resemble what Earth was like a long time ago. And so it's really about figuring out how all that chemistry turned into the biology that we have today, those early processes that might have led to life on Earth someday. And maybe they could be happening elsewhere out in the universe as well. And they're doing it with a rotocopter too, which is really cool. So
one way to find out. Yep, one way to find out, send a robot out there and get some, with a full scientific payload, get some data on what's happening and extend our knowledge of the universe is the deal. But let's get our guests over here real quick. Elysia, would you like to do the honors and introduce our guests?
So today we've got with us Dr. Elizabeth Turtle, who also goes by Zibby, so you might hear us referring to her as such. She's the principal investigator for the Dragonfly mission at the Johns Hopkins University Applied Physics Lab. She has worked on numerous planetary, I have an engine going on outside. She's worked on numerous planetary missions, including Galileo, Cassini, and Europa Clipper. And her research focuses on understanding how planetary surfaces evolve, and especially on icy worlds like Titan and Europa. We've also got Dr. Ralph Lorenz, who serves as Dragonfly's mission architect. He specializes in how spacecraft interact in planetary atmospheres and surfaces, and has worked on missions to Mars, Venus, and Titan. And he's also the author of several books on planetary exploration and flight beyond Earth. So we are so excited to have you both on here today with us. Welcome.
Very happy to be talking with you today. And I love your earrings. Those are wonderful.
Thank you. That's part of my thing. I love to theme them with, our topics. So, let's kick this off. Why Titan? Why is Titan such a compelling destination compared to other places, Europa and Enceladus? We know that there are, organic compounds out there. We're thinking these might be exciting places to explore for potentially building blocks of life. Why Titan specifically? What intrigued it? What intrigued you all about Titan?
We're really lucky in our solar system. We've got this really wide variety of bodies with different histories and different conditions. And so there are a lot of really complementary places to explore that can give us different insights into aspects of planetary origins and habitability. And Titan is really unique in that it has an atmosphere that's actually pretty unique for even planets. Titan's atmosphere is denser than Earth's atmosphere, and this atmosphere on Titan, where it's much colder in the outer solar system, is mostly nitrogen like our atmosphere, but then has a little bit of methane, which builds really complex carbon-rich molecules. And those molecules have fallen out of the atmosphere onto the surface. But Titan is an icy moon. And so at places where that a water ice crust has melted in the past, there's been the opportunity for this complex carbon-rich material to have mixed with liquid water in the past. And so we hope it will give us insight into the kinds of chemistry that can have occurred on this very different in this moon with a very different environment than Earth, but that has very similar chemistry to that of the early Earth.
That is fascinating. And so the idea then we've got these, liquids of things down there too, right? So is that why you guys thought having something flying might be better than like a rover or a lander of some sort? Or why specifically this octocopter idea, other than obviously it's got the atmosphere so it can support something like that? Or maybe that's the reason.
Titan's got, well, as I said, it's got an atmosphere that's 4 times denser than Earth's atmosphere. The gravity is 1/7 that of Earth. So it's actually physically easier to fly on Titan than it is here on Earth. And so that makes it a really natural way to explore Titan. And Ralph's worked with a number of concepts to take advantage of that atmosphere to potentially explore Titan with different types of vehicles. For Dragonfly, it's really great to be able to use a rotorcraft because we can actually interact with the surface, take samples, et cetera. And so it allows us to get to a variety of different places.
Yeah, one thing that's really quite special about Titan is something that Earth has as well, which is weather, a hydrological cycle wherein there's a fluid, in Earth's case water, in Titan cases is methane, that can exist as a vapor in the atmosphere and condense into cloud droplets and form rain and then pool on the surface and flow. So Titan's surface has been shaped by many of the processes that we have here on Earth, and you get a very complex landscape as a result. Somewhat familiar. I mean, you see some of the same things like river valleys and sand dunes, and there are impact craters and maybe some more exotic things. But they're made of different stuff, and maybe processes occur at very different rates, but the processes are familiar. And the fact that the landscape is complex means that different parts of the surface probably are made of different stuff, and we have evidence of that from the Cassini mission, which was flying by Titan for 13 years. And that means that to find the really interesting chemistry, the stuff that may inform us about the origins of life, we sort of need to go to the right places, or at least maybe many places. And then you get pushed into wanting a laboratory that can go from place to place. And you can do that on wheels. That's being done very successfully on Mars. But there are, challenges with getting over soft terrain, sticky terrain, and Titan's a relatively unfamiliar environment. But you can get over, literally, those kind of terrain obstacles by powered flight. And because Titan has a low gravity and a dense atmosphere, it's particularly easy to fly. And so Dragonfly is a very natural vehicle to do that exploration.
It's fascinating because we mentioned earlier, of course, Ingenuity. Everyone, I think, on the planet knows about Ingenuity at this point. It's an amazing technology demonstration mission, really.
Yeah, maybe you can bring up the Ingenuity picture.
Yeah. It was a demo, right? So that didn't actually take a payload necessarily in the way that this one did. But I'm sure it helped you all learn a lot about powered flight on other planets, right? So I'm curious, we've talked, actually, we've had two different episodes of Astro Live on Ingenuity. We talked to Teddy Zanetos, who we mentioned before, and also Travis Brown last year. So I'm just curious to start off here about this idea of this Rotorcraft. What sort of lessons did you all learn from Ingenuity specifically as a demo that you now were able to incorporate into this mission to be ready?
Maybe you can pull up the Ingenuity image.
We are working on it. Yeah, we'll get it in a second.
I mean, Titan and Mars are very different places, right? Whereas Titan's atmosphere is denser than ours, the Martian atmosphere is 50 to 100 times thinner, and so it's a very difficult place to fly. So for Ingenuity, the huge challenge was an aerodynamic one, right? How do you beat the air hard enough to develop enough thrust to balance the weight? And that basically was Ingenuity's only function. I mean, it had some cameras from which some really quite interesting science has come out, but it didn't have a to-do list of scientific questions. Yeah. So that's me holding a ground test unit of Ingenuity at the company that developed the rotor blades and many of the parts.
It's like a drone you can hold, like you can actually fit that in your hand.
Yeah, the thing weighs is it a couple of kilograms, 4 kilograms, I forget.
Yeah.
But actually, the idea of a rotorcraft on Titan's not a new one. The ideas have been kicked around for a couple of decades. And there was an artist I worked with, James Gary, to develop a sort of helicopter concept that's on the left back in 2000. So it's now a quarter century ago.
Wow.
And we thought, maybe a twin-bladed rotor, because those kind of pack fairly efficiently without the big tail boom that a conventional helicopter has, and long spindly legs to keep the rotors, well off the ground and away from rocks. And you can see those elements are actually in Ingenuity, partly for reasons of how it was delivered. And we imagined back then that this crazy helicopter might visit the Huygens probe, which was carried to Titan by Cassini and parachuted down in 2005. And the helicopter's looking at the sort of heroic corpse of the probe there with its parachute draped beside it. And actually, Ingenuity ended up taking a very similar picture of the heat shield and parachute of the Perseverance rover that took it to Mars. So in a way, the sort of fiction about Titan or imagination about Titan sort of preempted a little bit of what actually happened with Ingenuity. So the aerodynamic challenge is quite different, and the goals for Ingenuity were only to demonstrate flight, not to achieve a scientific function. But some of the operations and testing approaches that Ingenuity used in its development have certainly informed what we're doing, and we've had the valuable opportunity to have the Ingenuity team, present in some of our reviews and share some of their experience. But the whole sort of process of, what does the vehicle see or send back to us, and how do we react to that in planning the next step? A lot of that function has been very very useful to hear about.
Gotcha. Hey, on the top of Ingenuity there, I see the solar panels. We know that it sort of had the charger that would charge up its solar or its batteries with the solar panels and then go from there. How is Dragonfly going to get its energy, power?
Yeah,
fuel?
Dragonfly has a slightly different power source. Dragonfly actually uses the same power source that Curiosity and Perseverance use, which is a multi-mission radioisotope thermal electric generator, or MMRTG for short.
Yeah.
And like other missions, we use that to charge a battery. Flying, of course, as well as some of the scientific measurements, communicating with Earth take a lot of power. And so we actually have a very large battery in the interior of the lander. And we charge that off of the power that comes off from the MMRTG. And then we use that battery to do our primary activities, including flying.
Including flying, nice. Yep. Can I ask, I always think about, I don't have one in my garage to play with or anything. I don't know how much power they put out. How much power does the MMRTG put out? Is it 10 days of charging for 5 minutes of flight, or how does that math sort of work?
It's not quite. It puts out about 80, 90 watts.
Okay.
It's not a lot. We work to make everything very efficient. Titan's day is 16 Earth days long.
Right.
So we'll have a lot of time during the Titan night to recharge the battery. And we also do a lot of hibernating while we're between activities while we're charging the battery. The other thing that the MMRTG puts off besides power is heat. It's often referred to as waste heat. But in terms of Dragonfly, it's very valuable heat. The surface temperature at Titan is 94 Kelvin. So that is very cold.
I had to do the math in my head real quick.
It's almost unimaginably cold, right? It's minus 180 Celsius. And it means that we use every watt of heat that comes off of the MMRTG as well. We have an insulated vehicle, and we keep that heat in the interior of the vehicle so that all of the electronics, et cetera, are at the proper temperature to operate.
The operating
So there's an interesting contrast between Ingenuity and Dragonfly in that sense. Titan's atmosphere is very dense and very cold, so that's why we really rely on the heat from the MMRTG to function. But in fact, the Ingenuity helicopter could fly for 2 to 3 minutes. And that limit was not the battery on Ingenuity. They weren't energy limited. It's that the motor driving the rotors would actually overheat because the thin Martian atmosphere isn't thick enough to take the heat away. So the heat just accumulates in the motor and would eventually cause some epoxy to fail or something like that. So that's a limitation that the environment set for Ingenuity that we don't have. We sort of have the opposite problem. We have to warm our motors up before the grease is soft enough to actually let the rotors turn. So every vehicle has to be designed for its specific environment. And one of the things I do on the project is define what that environment is, in numbers for the engineers to do the detailed work.
Makes sense. So, Chad, folks watching, if you wonder, how much is 80 watts? You remember light bulbs? Back when we had light bulbs? Some of you are too young to know what a light bulb is, which is a really weird thing to say. But the power that the MMRTG puts off is around what a normal light bulb back in the day used to put out, like a 7,500 watt light bulb, right in that range, right? If you want to think about it in today's terms, you got your USB-C charger for your phone, and that's going to do 15, if it's fast charging, 20, 22 watts. So the entire almost vehicle-sized Rotorcraft is like 4 or 5 USB-C chargers running at one of the higher USB-C rates. So not a ton of power. It's not like a huge oil refinery on there making a ton of power, but it's enough to fly Dragonfly in the Titan atmosphere. I have to ask, the atmosphere is a lot more dense, right? And when we talked about Ingenuity, it needed a really sort of these big rotors and this really fast RPMs on the rotors to fly. Here, do they go more slowly? Like, is it like whoop, whoop, whoop? Or what is it like to fly in a thicker atmosphere?
So the rotors will spin at about 1,000 RPM, 20 revs a second. So they are, whipping around. But the combination of the dense atmosphere, 4 times denser than our air, and the low gravity means that if you just took, a given vehicle and took it from Earth to Titan, it could hover with 38 times less power. So, it's transformationally easier to fly on Titan than on Earth.
Is it, okay, this is a silly question. Is it more like swimming or more like flying because it's so dense?
No, it's still flying.
Still technically, still a gas.
Venus is getting there. The Venus atmosphere is like 50 or 60 times denser than air, whereas water is 1,000 times denser or 800 times denser. So, Venus is starting to get to swim territory, but Titan's flying.
Still solidly in the flying territory. I saw a question come through chat in Elysia. I'll get you for a question next. Somebody asked, why is it called an octocopter? And I think the image that we have right here helps explain that, right?
Yes, yep. It's got 8 rotors.
8 rotors. How big are the rotors?
The rotors are about 1 meter in diameter.
1.4 meters, yeah.
Thank you. I think there's a picture with the name Rotor in the title that shows someone holding one of the rotors.
They're the same size as Ingenuity's
exactly,
rotors, more or less.
Oh.
Yeah.
So it's like 4 Ingenuities. Well, it's 8 rotors. And this quadcopter, Ingenuity is the single double stack, like the coaxial rotor, I guess, right? So it's like 4 Ingenuities. 4
pairs. Exactly. We have 4 pairs.
Gotcha.
Yep. Of 3-bladed rotors.
3-bladed rotors. So again, Ingenuity was 2 blades, right?
Yeah.
I think so. Okay. Gosh. Looking at this picture, they're tilted a little bit. Can we talk about why they're tilted? Is that like an interesting engineering thing as to why they're tilted? Or is that like, so it clears the landing gear? What?
So, there's maybe three tilts to talk about here.
Okay.
The tip of a spinning rotor goes faster than the inboard part, so you actually tend to have a twist, right? So that the inner part has a bigger angle of attack. It hits the air more steeply, so even though it's going slower, it pushes the air down more. Whereas that would cause a lot of drag right at the tip, so the angle becomes shallower towards the tip. So that's the twist of the rotor.
Okay.
And varies the angle of attack across it. Dragonfly's rotors are actually canted. They're not perfectly coaxial, and that's to give us a little bit more yaw authority. Gives you a little bit more ability to turn in the horizontal plane by changing the rotor speeds.
We call it the Vader configuration because it kind of looks like Darth Vader's TIE fighter.
Nice.
The Vader configuration. I guess that way, if you tilt it or cant it is the right term. Thank you. If you cant it a little bit, it's not just about the inertia, the changing speeds of the rotors. Like if you see a little drone on Earth, sometimes those things turn just by spinning 2 rotors faster and spinning 2 rotors slower, and the differential makes them turn. Here, if you cant them a little bit, you get a little bit of, I guess, aerodynamic control.
Yeah, we're actually directing a little bit of the thrust sideways is the way to think of it.
Aha, that's a good way to think about it.
I mean, that's kind of like a helicopter, right? Like their blades are also kind of tilted. I think also ceiling fans also have a slight.
So
don't they?
with a helicopter, you have the subtlety that you can change the angle of attack
Right.
as the rotor spins around. In fact, there's a faction in the rotorcraft industry that would maintain that we don't have rotors at all. That a rotor is only worthy of the name rotor if it does this.
My goodness.
Where's your swash plate? Like, come on.
Yeah. So ours are just propellers.
Oh, goodness. Fighting words. Geez.
Yeah.
Chat, what do y'all think? Are they rotors? Are they propellers? Let's see if chat has any opinions on this.
You're going to a whole nother world. So, like, I think you guys.
Yeah.
Can follow
I mean,
whatever
it's
you
like
want.
the whole, what's a planet, what's not a planet.
Yeah.
Sure.
Yeah.
Yeah.
Nomenclature gets people very worked up.
If you'd like to correct him, you can go to Titan yourself, and you can change the label on the craft, saying, "Oh, this is actually a propeller, not a." If you can do that, then you're allowed to name them whatever. The team that puts the spacecraft there can call them what they want, I think. Elysia, did you have a question?
Yeah. So sure. So, you mentioned that this thing is gonna go there. It's gonna fly. It's gonna land. It's gonna sample. It's gonna fly. It's gonna land. It's gonna sample. Can you talk a little bit about just some of the engineering hurdles of doing that? I know Ingenuity kind of also sort of hopped around like that, but you're also sampling now, and with I just keep referencing Ingenuity because it's all I have as a frame of reference here, but. It was using its cameras and looking at like shadows to see where it was a good spot to land, but then that kind of backfired also, and it sort of crash landed there at the end. And so, how are you guys using that to see where you're going, knowing where to land, the sampling aspect of it, and can it if it were to like land kind of sideways, can it help itself back up, or have you thought about any of that stuff as well? It's a lot of questions.
It's like, Elysia, I have a question. It's more like 4 questions and 3 observations.
Let's talk about any of that.
Yeah, I mean, it's an environment that we've explored with Cassini-Huygens. So that mission, the Cassini orbiter, was at Saturn for 13 years and did 120 some flybys of Titan and mapped out the surface of Titan. So we have that information about the general environment and where the types of materials that are of interest for Dragonfly to explore and to sample are. So we're starting kind of from a medium resolution map, if you will. We don't have high rise, MRO at Titan to do very high resolution mapping, but we've got we have the medium resolution map, and then the Huygens probe, which descended down through the atmosphere in 2005 and made measurements of Titan's atmosphere, and then sent back a view of the surface that it landed on. And one of the really important things of that, and one of the things that Ralph's been translating into the requirements for Dragonfly, is that the timing of Dragonfly is such that we get to Titan 1 Titan year after the Huygens probe was there. So we actually know the atmospheric profile at that time in Titan's year.
Okay.
And can use that to design aspects of the lander. But there's a lot of, as you can imagine, there's a lot of work that has gone into aspects of both the thermal design for such a cold environment, the mobility, and the fact that, Saturn and Titan are 70 to 90 light minutes away. So it takes one-way, the one-way travel time to communicate with Titan is 70 to 90 minutes. So everything has to be autonomous.
Yep.
So there's a lot of work that's gone into that. One other aspect that we've been able to really leverage existing technology is aspects of the payload, where a lot of the instruments have heritage, as we call it, are designed based on the designs of instruments that have been sent to explore on other missions. And so there's a lot we were able to leverage in terms of existing technology, and then a lot that has gone into designing Dragonfly specifically for the Titan environment.
If you bring up that Dragonfly bottom view you had, I can speak to the question Elysia had. You can see there's some sort of square windows. There's a camera windows, and like Ingenuity, we use successive images of the surface to figure out how we're moving across the surface. But the 2 little circular windows are for a LiDAR, basically a laser radar. that can map the surface heights and detect, if there's a gully or if there's a rock that would present an obstacle to safe landing. So on the ground, the science team, the operations team will figure out the plan and say to Dragonfly, fly 1.5 kilometers, northwest, and take some images and then come back, or land there, whatever. But because we're 70 light minutes away, we can't joystick the thing, right?
Right.
It has to actually figure out, where it is, and it does the hazard detection, or hazard mapping autonomously, and will basically score the terrain. Is it sloped? Is it flat? Are there rocks? And keeps in mind, where the safest place to land is, as near as possible to where we've asked it to land scientifically. So, there's sort of different levels of autonomy in that sense. I don't know if you're able to bring up the port side view to talk about the sampling system.
We can. It'll just take a second.
There we go. Okay.
It'll take less than a second, I guess.
Yeah, great.
Kevin's on the ball.
You can see there's lots of complex things on here. I mean, this vehicle, different engineers of different flavors, have their own, aspects to worry about, and they see a complex system like this, through their own lens, right? So if you're worrying about communication, every bit of data, every pixel in a multi-megapixel image has to come 1 billion miles across the solar system. And so we have this roughly 1 meter circular antenna on the roof that we point at the Earth, right? There's no relay spacecraft at Titan like there are at Mars. Every bit has to come direct from that antenna, which tracks the Earth in the sky, and then folds down for when we fly, right? You don't want to fly with it
up. I was wondering, while it's flying, is it constantly turning towards the Earth, or it will land, it'll redeploy the antenna, it'll home in on Earth and get it realigned and that sort of stuff, and then start sending you the data. But it doesn't have a local hop like Ingenuity had the rover it could talk to, and I think right. Ingenuity could talk right up to one of the Mars orbiters, right?
No, it relied on the rover. It could only talk to relay. Them. Yeah.
Okay, so here, your spacecraft needs to talk all the way back to Earth, and it's not just at Mars, it's all the way out to Saturn. Real quick, I saw some conversation in chat. When we said Venus earlier, that was just an example of atmosphere thickness. This is not going to Venus. This is going to Titan, which is a moon of Saturn. So I just saw some people talking about that in chat. I wanted to clarify that real quick. I have a question. How do you test this? What do you do? Go to Antarctica and make a box and open a propane cylinder in it, and then it pressurizes and you try to fly your... how do you test that sort of environment?
Yeah, there's a DragMet testing slide you can maybe pull up. Okay. So, you can't replicate Titan completely, right? You could get various things right, but you won't get the gravity right.
Right.
We have a chamber here at APL that we can... bring down to Titan temperatures and push in extra nitrogen to bring it up to Titan pressure.
Okay.
So for things like, the box at the left there inside the chamber has wind sensors, right? I have a meteorology package, and turns out to be easier to actually spin a frame with the wind sensors on it around in Titan air that's still than it is to have a blower to push the air, but
to move it around.
So there we're doing kind of a fairly authentic test, but there are other circumstances. For example, some wind tunnel stuff for the aerodynamics of the vehicle. There's a wind tunnel at NASA's Langley Research Center where we have a model of Dragonfly in right now, and it's actually a tunnel designed for transonic tests, but we use it very, very slow. But they can fill the tunnel with a freon, a heavy gas that gets us most of the way to Titan conditions. It's not Titan temperature, but It doesn't need to be, because the test is about drag coefficients and stuff. We need to do things like test some of the systems for exposure to dust. we're going to land among sand dunes. There may be dust blowing, sand moving. We have to test some materials for abrasion, right? But it's abrasion not at room temperature. It's abrasion at minus 183 Celsius.
Right.
So we actually had a robot kind of drag some of the materials across an abrasive in liquid nitrogen in a cooler. So you have to sometimes just do the best that's practical.
Yeah.
It's not a completely authentic replication, but of course with a rotorcraft vehicle, we have the opportunity also to fly in Earth's atmosphere, not with the whole vehicle, but with a reduced scale model, and maybe some graphics can go with that.
Yeah, there's a test video. There's a test flight video from a test we did in the Imperial Dunes with Rotorcraft,
and that lets us rehearse the operation of the autopilot, for example, and this measurement of ground speed by camera imaging. And we actually do that at kind of twilight conditions because, on Titan, there's much less light than there is on because it's so far from the sun.
And how's the contrast work when there's less light? And yeah.
We can do a lot more than a rocket-powered vehicle, right? The sky crane that delivered the Perseverance rover, right? That never was tested, right? It was just there was lots of simulations and lots of bits were tested, but the sort of big assembly was never exercised on Earth. But we can do that to some degree with a drone vehicle and fly it over representative terrain. This is the Imperial Sand Dunes in Southern California.
Yeah, I see a lot of. Go ahead, ZB. Yeah, sorry.
I was just going to say, Ralph was talking to a picture of the smaller chamber that APL built. There's another one under the folder that has the testing pictures with the Titan. It says Titan chamber in the title, and that's the larger one. So that's still the small one. So it's about 5 feet in diameter.
Right.
The one that says Titan chamber has the large chamber. There you go.
Oh wow!
So that chamber was built to test the full scale, or in fact the flight vehicle. The flight rotorcraft will go in that. And what you see in the chamber in this picture is a full scale development test model is designed to test the thermal aspects. So this chamber goes down to Titan temperature, but it goes it doesn't go up in pressure. It actually goes down in pressure as well to match the convective environment that Dragonfly will feel at Titan under Earth's gravity. So there are a lot of different things we've needed to do in terms of the testing to tailor the environment to be able to, as Ralph was describing, measure and test different aspects of the lander and different aspects of the Titan environment.
It looks like the world's largest mini fridge.
Yes.
The world's largest dorm fridge with the one door on it,
Yep. Except you need a vehicle to close that door.
Is it like a truck or something? A golf cart?
Yeah.
Really?
Yep.
Wow. Like the whole team just pushing on the door really hard.
Yeah.
Good team building exercise. And if you go to there's the picture with Langley in the name. Oh, there's the team with the test flight vehicle.
Right, the smaller scale test flight vehicle.
There you go. Yep. This is it's half of it, but it's the full scale vehicle. That's down at Langley's Transonic Dynamics Tunnel, and so that gives you a sense of the scale of the vehicle. And as Ralph said, there's a test team down there right now. That has been doing another test in that facility. So we've been able to take advantage of a number of the NASA wind tunnels, which has been really valuable to test and demonstrate different aspects of the aerodynamics and the flight we'll be doing on Titan.
And the blue bits on the model there are actually the sampling system. The sort of this big drill at the side. So the way we get surface samples isn't with an articulated arm. Which would be complicated and heavy, and you'd need to warm all the joints.
Right.
The drill is actually relatively simple. It just kind of goes down.
Just
the
one
clever
axis.
Part, is that it's actually a hollow drill, and we suck Titan atmosphere through the drill, through these slots, and it drags particles of the cuttings from the drilling basically to the scientific instruments.
It's like a drill and a straw.
Yeah, exactly.
Straw drill.
So that was
straw.
a kind of neat way of exploiting the environment again.
Yeah.
To use Titan's atmosphere to convey the sample, quickly, and it keeps it cold so that the drilling doesn't melt anything. It's really a very innovative approach.
Yeah, we've got a couple pictures. Real quick, we have a couple pictures with the team members. How many people are on the team working on this? There's a question in chat.
Oh, it's a very large. Any mission has a lot of people working on it, right? People with different skill sets to design this. So this is a picture from our team meeting a little over a year ago, and there are I'm sure well over 1,000 people with different at different institutions across the country, around the world. We work with people at different NASA centers. In fact, most of the NASA centers are involved. A number of government laboratories, industry. So we have a wide breadth of experience and expertise, as well as skill sets. Right. We like to. We always think about planetary exploration or space missions. We think about engineering and science, but there are also a lot of other skill sets that go into proposing and developing a mission. You've seen a lot of the graphic design, a lot of the artistic renderings the team has been doing. There's obviously a lot of programming, a lot of software, autonomy software, et cetera, that is being developed. There's a lot of writing that goes into being able to communicate about the mission within the mission to NASA, and then of course publicly as well. And that's one of the things that's really fun. It's a really wonderful team sport where you get to have people playing all the different positions, and you get to work together, and everyone's working toward this common goal of exploring Titan.
We see that so often where there's so many different skills required on the team. Like if your skill set is driving a vehicle that closes a refrigerator door, guess what? There's room for you on the team. Elysia, I'm so sorry I interrupted you for my joke.
So many things I want to say.
Go.
No, I mean, that's a great thing to highlight, though, Zibby. Like, we are always talking about how there's so many different careers involved in space, right? It's not just astronauts. They get all the hype. They get all the celebrity. But that's why we do shows like this, to talk to people doing amazing things. You guys, awesome job, with all of this stuff. We've got scientists and engineers all the time. But thinking about these other people, too, these communicators, these artists, right? Everything we're looking at right now, these are artists' renderings, right? We've never done this before. We don't know what Titan actually looks like other than the Cassini images, right? So seeing this thing flying, these animations, if you have a graphic arts skill set, I mean, this could be for you as well. If you happen to like space, or even if you don't like space, if you just want a job doing graphic design, hey, why not? You could design what a rotorcopter looks like on Titan.
So one of the most fun exotic skills I've seen used on Dragonfly is origami. There's the drill stage has a sort of concertinaed plastic cover to keep dirt out of the gear and the track. Yeah. And it turned out that it was an origami problem of how to fold this flexible thing so that it would deploy smoothly and retract.
It's like a bendy straw.
James Webb too. James Webb also had that unfolding thing as well. Right. So there's so much thought into that. I always also like to highlight, just going back to art too, like the JPL travel posters that they made. We were talking about that earlier. They did this just to kind of get excited about these amazing foreign places that we've never even dreamed of visiting, or we have dreamed of, I guess, but we haven't actually done them. But Titan especially, right? Like they made one that is specifically about Titan, really highlighting all of the rivers and everything with all the methane. And it just really gets your imagination going of what it could be like once you actually land there. So that's a really cool thing. I want to actually go back to the sampling though. Specifically, now you're talking about how it's going to be landing and drilling. That was one of my questions earlier. I was going to ask, are you actually going to be picking up samples, and when you have them on board, because you answered that already, are you just going to be kind of like scanning them, looking at them, and then dropping again, or are you actually storing them to potentially be retrieved later if somehow they could, make it come back home?
We have a mass spectrometer, so an instrument that's able to, like the Curiosity rover on Mars has a very similar mass spectrometer, actually, and it's an instrument that, when you give it small samples, can so we're not picking up that much of Titan, can measure the composition and then the structure of some of the molecules that are in the materials, the surface materials that we'll sample. So that's the reason for picking up the samples, is to really get at the detailed composition. One of the big questions that remains after Cassini is what the surface composition is. It's hard to measure from orbit, because you can't do these very detailed spectral observations because of the methane in Titan's atmosphere.
Right.
And so this will enable us to actually make those detailed compositional measurements. But we're not storing samples the way Perseverance is for future retrieval. This is a self-contained laboratory, and the data will be sent back from the measurements that the mass spectrometer makes. So all of the analysis is done on Titan.
And you had that map, right, that you showed us of what Cassini was able to take pictures of, and if you've mapped out the surface.
Yeah, if you bring up the Selk image.
Yeah. So I'm curious, we on Mars, we were really interested in Jezero Crater, right? It was maybe a former river delta, there was maybe old water there at some point that boiled off or something. What is scientifically exciting on Titan? Like, what areas are you guys specifically hoping to look at, and what are you hoping to find in those particular areas with the samples?
All the areas are particularly exciting.
Okay.
Any of Titan would be exciting. But the picture on the left is a Cassini radar image. It's about 150, 200 kilometers across, so 100 miles, from left to right. So you see that big square thing, that's a crater, an impact crater, or by an asteroid impact millions of years ago, presumably. It's 80 kilometers across, and why it's square, we don't know. I mean, it's not as round as it should be.
Yeah.
Meteor crater is actually somewhat square because the pre-existing faults in the rock guided that. So when the impact occurred, there was likely a lot of alteration of the surface. I mean, excavation mechanically, but probably also melting. And Titan's crust, as we understand it, is mostly ice, water ice. And so the stuff that melted was liquid water. And that's kind of a key ingredient. Titan, we know, has lots and lots of organic, carbon-bearing, hydrogen-bearing compounds, but very little oxygen. But on the surface, if this stuff is exposed to water in this impact event, then there's a whole sort of new generation of chemistry that occur. And we presume that on Earth there was some state of the planet that was non-living, that was complex chemical systems, and somehow those systems acquired certain functions, the ability to generate free energy, to store information, to replicate that information. And we don't know how easy it is to make that non-living to living transition. We don't think that's necessarily happened on Titan. But some of those steps, those chemical evolutionary steps of increasing complexity, have happened and are sitting there frozen, perhaps around the crater, for us to try and diagnose. Now, craters are rough places typically. Yeah. So rather than land straight in the crater, what we're going to do is land in these stripes, dark stripes towards the bottom of the image, and these are shallow sand dunes. The picture on the right is some dunes rather like them, we think, in Egypt, but there are others in Namibia. The Namibian ones are a bit bigger. But these large dunes have typically flat areas between them that will be very safe for us to land. So we'll land among the dunes first and see what the sand is made of, and maybe the stuff between the dunes, maybe we'll get a sniff there, and we'll work towards the crater and hopefully sample progressively newer, different materials. And I'll let Zuby speak to the Namib picture here.
Oh, this is a picture of the Namib Desert, which is actually a really good analog for the type of dunes that we see on Titan. So they're not the dunes that we're used to seeing at the beach, maybe, where the sand is kind of, where the dune kind of moves in the direction that the wind is blowing. Here, the sand propagates along the dunes. And so what you're seeing is these darker red dunes and then these broad, lighter colored interdunes. And you get, that's the same kind of thing we see on Titan. And in fact, the dunes on Earth are about the same scale as well. They're a few kilometers apart.
Wow.
And they're about 50 meters or so high. And that's pretty similar to what we see on Titan. Now, on Earth, this is all silicate material. It's silicate sand, but on Titan, the dunes are made of organic material. We don't actually know how Titan makes organic composition sand. It's the same kind of size as our sand grains here on Earth, but the composition is very different. So that'll also be an interesting thing to learn. If you go to the picture that says interdune in the name, you'll see one of the other reasons that is good, that it is convenient to have this kind of place to land in, and that is because the interdunes are very flat.
Yeah.
And so this is in the Namib Desert. There's a person there kind of walking in the interdune. There's a lot of wide open space. And if you're designing a vehicle to land on another planet, this is the kind of landing site you want, where you can actually, you have this broad, flat area. And that also on Titan, these interdunes may have a water ice composition that's reflects the primordial crust of Titan.
Right.
And so that means we have materials that are very different in composition and close proximity to be able to sample with Dragonfly as well. So it's a great initial landing site. And then as Ralph showed, the dunes, there's an area of dunes just to the south of this impact crater that allows us to get into the deposits associated with the impact crater.
Yeah. Looking at that, I don't see a lot of, it's nice and flat. There's not a lot of obstacles, but there's also not a lot of obstacles, right? There's not a lot of distinguishing features that you can look at and figure out where you are, how far you off the ground. And that's one of the things that Ingenuity sort of ran into when it got into the dune area. It saw sand, but there wasn't, if I remember correctly, there wasn't enough contrast or difference or identifying marks for it to really know how high it was, because it was only doing vision navigation. You mentioned the LiDAR, sorry, I always say that wrong. Is that something that can help avoid sort of Ingenuity's eventual, I'll say success, not demise, because you have those other instruments, or have you taken information from what Ingenuity learned to apply it to this when you see these big open dune areas?
This is one of those areas where you can never say something is impossible.
Right.
I mean, we carry a risk. We manage risks on a project like this by everyone thinks of anything that worries them and writes it down and says, okay, how likely is this? If it happens, how bad is it? What can we do about it? And how much does that cost? And, some things you decide, we'll have a spare battery, spare
right.
thing. You can't have a spare, well, you can have a spare parachute, I suppose, but you can't have a spare heat shield, right?
Right.
So some things, some risks you just have to accept. Bland terrain that can't correlate in the image, it is theoretically possible, and it was encountered by Ingenuity.
Mm-hmm.
These image correlators that do the sort of automatic matching of one image to another, they do amazingly well. I mean, there's an image, a scene that looks completely bland to your eye that these correlators will pick out. The LiDAR by itself actually won't help us a lot in this regard. But even though Titan's atmosphere is hazy and so the illumination is fairly diffuse, any surface corrugations develop a little bit of shading because of the shape.
Right.
And so we're pretty confident that most everywhere we will go, there will be features to match up with. And obviously we have to sort of guess everything right now, but as soon as we make the first landing in one safe place, then we'll have so much more information to work with, and can do workarounds of avoiding particular areas or whatever.
It's not entirely boots on the ground; it's sort of skids on the ground, right?
Exactly. Yeah. Yep.
Go ahead.
Another test that we've done. We actually used a terrain model from the Namib Desert as input to the navigation software. We had to they had to edit out they're not a lot, but there's some plants in the NAMIB, and they had to edit out the plants because we're not going to have that kind of thing to navigate off of on Titan. But it does look, as Ralph said, it looks really quite bland, but the navigation software is able to work with that and find these subtle differences to be able to do the navigation autonomously.
So when you land on these bland Dune areas,
sands, you could say bland sands.
The bland sands. What are you guys hoping to find there? Like you mentioned, like organic sand. Like what are you looking for specifically? What is that?
Well, we want to understand the chemistry that has occurred on Titan. And by being able to go to different environments with very different geologic histories, that will give us different perspectives, different context for the types of chemistry there. And the sands may be very widely sourced from, regionally or even globally around Titan. One of the Mars landers, Mars Pathfinder, specifically went to an area where a lot of material had been brought together by water flowing over the surface, because it gives you a wide variety of materials in a localized area. The sand on Titan may do something similar in that it may be very widely sourced. So that will give us a really good sense of the kinds of chemical complexity, and then by being able to compare that kind of the compositions of the sands, for example, to the compositions of materials we see near the impact crater, where the carbon-rich material may have interacted with liquid water in the past. That'll be a really interesting comparison to see what different kinds of materials you get in this environment that had liquid water in the past, right? Like a primordial soup, if you will, out in the outer solar system. So being able to compare those materials is going to tell us a lot about the different types of chemistry that has been able to that has occurred on Titan.
And there's a couple of aspects we will look for in particular. I mean, living things have chemistry that isn't random, right? It's not that you just chop up carbon, hydrogen, oxygen, just stir them all together and they appear randomly. Life favors certain metabolic pathways. Like you look at the fatty acids in sheep fat, right? In wool. And they have even numbers of carbon atoms. The chains are all even numbered, not odd numbered, because the pathway adds 2 carbon units at a time. So there's some of those sort of abundance patterns are characteristic of some of the chemistry that goes into life. Another aspect is that there are some molecules like sugars or amino acids that have a sort of handedness. They can come in sort of mirror image pairs that have the same molecules in each, but you can't superpose them. Right. And it turns out that life uses one of those hands. All of the amino acids in our proteins are all left-handed, I think, and sugar's right-handed. Whereas you look at meteorites and abiogenic sources, they have equal numbers of both. So if some chemical environment on Titan produces lots of one side and not the other, then that's telling us something very interesting about how that selection starts to happen.
Right.
We recently, well, not us, but NASA, I guess, with Bennu, right?
Royally.
Like they recently discovered that there's like essentially the blocks of RNA and sugars and stuff on Bennu.
Yeah.
Was this really exciting for you guys to hear, to be like, oh wow, like that's kind of what we're looking for too?
It was.
Like, yeah.
I mean, it's been surprising, I think, how rich these asteroidal environments have turned out to be in terms of organic chemistry. But that immediately raises the question, well, what different flavor of organic chemistry, what different set of compounds will an environment like Titan give us? So we're very looking forward to sort of, building on that comparison.
Do you have, as principal investigator, Zibby, do you have like a hypothesis of what you think you might find, or are you just kind of like we're gonna see what happens and then go from there.
We do have a lot of hypotheses. Dragonfly is also a mission of exploration, and so like I think almost every planetary mission, I'm sure there are going to be things about Titan that surprise us. But we know from measurements by Cassini. Cassini also carried a mass spectrometer, and it sampled the very top of Titan's atmosphere. So Titan's atmosphere is very extended. The gravity is low. There's a lot of atmosphere there. Cassini's flybys were mostly above 1,000 kilometers altitude, and even at those altitudes, the mass spectrometer detected very large molecules. And we know from remote sensing as well that there are very large complex molecules there. So we, in terms of the size of the molecules, the Earth is really the only other place that has molecules of that size. And then of course larger, because we do actually have DNA and and the biological aspect as opposed to the abiotic process. So what we want to learn is what when you put all those pieces together, what kinds of products, chemical products are generated, and are there biologically relevant molecules generated, like amino acids and proteins, on the surface of Titan. So we can there have been lots of experiments done where you take all of these pieces together, these kind of chemical pieces together, and you can look at the kinds of materials that are created. But what we don't have the advantage of that Titan does is time. On Earth, when we're doing laboratory experiments, you can do them, over very short periods of time. But Titan, these materials have been mixed together for thousands, tens of thousands, hundreds of thousands, maybe longer of years. And so there's been a lot more opportunity for interesting chemistry to occur.
Wow. Really quick, I see some conversation. I'm not a chemist, but let's make sure everybody understands the difference between organic and biological, right? Like when you say there's organic sand on Titan, that doesn't mean like you go to the beach and there's that black sand and if you step in it, it smells because it's dead shellfish or whatever. That's not what you're talking about when you say organic sand, right? Can you tell the difference?
Carbon-rich or hydrocarbons, molecules that have, carbon, hydrogen, etc. in them, but they're not biologically produced necessarily. So we're using kind of a shorthand for that.
Right. We're talking
That's
about
not to say that Titan doesn't smell bad. It might.
I mean, it's methane, so.
I think that's one thing that people sort of don't really get. Like when we say organic in chemistry terms, we're talking about the molecule or the atoms and molecules that sort of make it up, not that it was generated by a living thing. And on Earth, it's like organic, it's free range, grass-fed sand on Titan. No, that's not what that is. Different types of organics there.
Yeah, different use of the word.
Yeah, exactly.
Not alive.
Yeah. Why are we going to Titan? It sounds like it has a lot going for it. It's got a thick atmosphere, low gravity. We've sent other missions to the neighborhood, so we know a little bit about it. Were there any other options that you might have looked at to go to, or was it just like, nope, it's Titan, that's where we're going?
So, I mean, Titan, as I say, has this sort of, extra dimension because of the atmosphere and the hydrological cycle. But this graphic's actually perfect. There's been a realization in the past few decades that a lot of the moons of the giant planets, so-called icy moons, are also ocean worlds, in that there's enough heat coming from the radioactive rocks in their interior that the inside or parts of the inside can be warm enough that the ice melts. So there may be a liquid water ocean under the ice on Europa. We've basically seen it spray out into space at Enceladus. Titan is big enough that it probably has an ocean under the ice as well. Although actually there's some scientific debate about that right now. But because of the atmosphere, Titan's actually the easiest ocean world to land on, because we can use a heat shield and a parachute. We don't need big rockets to do the landing. And so our first opportunity to explore the internal structure of an ocean world will be Dragonfly at Titan. And this is very unusual for a rotorcraft, but we have a seismometer. It's actually a contribution from Japan. We lower it with a little winch from the belly of the lander onto the ground. And if there's seismic activity and the orbit of Titan around Saturn is such that tides probably cause some, the seismic waves will rattle around in this ice shell in a way that will let us tell quite easily if such waves are present, how thick that shell is.
Right.
And that will be the first sort of, ground truth measurement of the internal structure of an ocean world. Now, is there anything swimming around in that water? We don't think so. It's a whale song. Maybe the seismometer will pick that up. But this will be a really important anchor point for understanding how these worlds evolve.
Yeah, so if it has a subsurface ocean or reservoir or whatever you want to call it, just the way that seismic energy waves pass through it because it's changing mediums. I forget the terminology where it changes, boundary between two mediums, and it changes a little bit when it crosses that boundary. And your sensor can pick up things like that, and you can only tell, is it there, but how thick is the shell? Maybe what it's shaped like. Is it a little different over here or there? I mean, all that with just landing and dropping an actual sensor. I say an actual sensor.
So it does depend on Titan cooperating with large enough Titan quakes. Titan has not signed our requirements document, so it hasn't signed up to provide large enough Titan quakes. But if it does, and as Ralph said, right, during the orbital cycle, we expect that there will be stresses in the shell that may cause that kind of seismic signature. So we're optimistic, but really, so we're really looking at trying to understand the level of seismic activity that one gets in an icy satellite. But if Titan cooperates, then yes, then we can get at aspects of the interior structure, which will be absolutely fascinating.
Is that like a one-time drop-off, like a sensor that is deployed and then you leave and it stays there, or does it like go down and then get retracted again and go down, and like does it stay with the vehicle?
Yeah,
it does.
Yeah.
Okay.
Yeah, we winch it back to hold it securely before we fly again.
Gotcha. So you sort of let it go down and make contact, and then you retrieve it and go. You don't want it swinging underneath. That'd be some interesting seismic waves. But then you land at another place, and you could potentially deploy it again. And if Titan cooperates, like you said, you might pick up something on it.
And we really do spend most of the time on the surface, right? With a long day, with Titan's day being 16 Earth days long. We are likely to fly once every Titan day or every other Titan day. And so this means that we're really spending almost all the time, like more than 99% of the time at Titan we're sitting on the surface making measurements. So that gives us opportunity to have the seismometer on the surface to listen for Titan quakes over extended periods of time. Our flights are about 20 minutes or so. So yeah, wow. We're on the surface almost all the time.
And how long is the entire mission duration for this now? Like, what is the whole of Dragonfly, or is it just until it doesn't anymore?
So the nominal mission duration at Titan is a little over 3 years, 3.3 years, just 74 Titan days.
That's great. And remind us again, when is this all planned to happen?
So
the launch and landing and everything.
Yeah, so we're scheduled to launch in July of 2028. So that is coming up very quickly. We're getting ready for our integration and test campaign with the lander coming up in 2026. So there's a lot to do in the next few years. Then it's about 6.5 years to get to Titan. So we launch in July 2028 and we arrive in December 2034. So 9 years from now, we will be.
Oh my gosh.
Yes, we'll be arriving at Titan.
Patience is a virtue when going to the outer planets.
Definitely requires.
I mean, it seems like a long time, but I started my career working on the Huygens probe in the European Space Agency, and when you're 22 years old, working on a project where 6 years after you start working, it's actually going to get to the launch pad, and then another 7 years is going to get to where it's going. It just seems fantastical and remote, but it happens sooner than you think.
Yeah.
But that's exciting too. It's inspiring for people, watching young people out there.
Absolutely.
You're in high school right now and you're excited by this. In 9 years, you'll be out in the industry doing this stuff. So maybe you could be working on this exact project in 9 years. That's mind blowing. Wow.
It really is cool. I'm looking through some chat questions here, and going back to something we said before. ZB, you said it's not like the grains of sand, like the grains of sand on Titan are not like something or are like something. How do we know what the grains of sand on Titan are like? Like, what evidence did we observe that says, oh yeah, they're shaped like this, or they're smooth, or they're round, or whatever? How do we know?
Well, I'll actually let Ralph speak to that because he's one of the people who did that work.
Okay.
Well, I mean, we know what the surface material was like at the Huygens landing site. In fact, the thing I did for my PhD work was design this little sensor, or a penetrometer that jabbed into the ground to measure how hard it was. So we know there the material was relatively fine grained. I mean, less than a few millimeters across. We rely on interpretation of some of the Cassini remote sensing data and sort of analogy, right? To make a sand dune, the stuff has to be able to be blown by the wind and make little hops. So it can't be cricket ball, baseball size stuff.
Yeah.
Is it 2 millimeter grains? Is it half millimeter grains? That's a little bit more open for debate. So we have to design Dragonfly with a lot of flexibility, which is hard, right? Because if you're an engineer, you want to know the specification of what things are going to be, and the narrower that specification, usually the easier it is. But we're like, well, we want to go to sand dunes, and then we want to go to a crater, and so that is an interesting challenge to anticipate some of these things. We adopt the hypothesis that some material will be water ice at 90 Kelvin, and you can pour water out and freeze it in liquid nitrogen. We've done tests with the drill system on that sort of material. Some of the organic stuff, is that like paraffin candle wax, or is it much harder? Well, if it's harder, then it's a bit like ice as far as the drill is concerned. But the soft stuff makes bigger cuttings. So that's been a challenge that the drill system has had to address.
Gotcha.
But you're right. The challenge is, this is a mission of exploration, and that means we don't know everything up front. We just have to make educated guesses.
Right, and prepare for a little flexibility, so when you get there, you can roll with the punches is probably not the exact right analogy, but
Well, and we have a suite of instruments designed to make measurements of the different aspects of the environment as well. So we will be taking samples and measuring the detailed chemical composition, but we also have a suite of cameras that will give us views around the lander of the geology around the lander. We'll have a very high resolution camera that looks at the sampling site, at the size of the sand grains. We have not only the seismometer, but a full suite of meteorology and geophysics sensors to get at different aspects of the environment. Just like a weather station, right? Temperature, pressure, wind speed, etc. And then we have a gamma ray and neutron spectrometer that allows us to do a bulk elemental measurement of the surface composition beneath the lander. So these are all designed to work together to give us information and put those samples that we get the detailed composition of into the context of the Titan environment. And that will also help us understand surprises and things that come along that we're not expecting, because we'll have a few different ways to study that.
What sort of weather are you expecting? Like, we talked about Titan quakes. That's not really weather, that's geology. But are there like Titan canes or Titan snow? Like, what are we expecting weather-wise?
Titan's atmosphere is actually really sluggish because it's denser than ours, and the time scales are longer, right? The year is 29 and a half Earth years long. The day is 16 days long. So Titan is almost isothermal, right? The temperature change from day to night, from summer to winter, is about a degree, right? So we're used to here on Earth really big temperature changes and dynamic winds and things like that. And on Titan, we don't have that kind of diurnal temperature variation driving it. We do have seasonal changes, again, not really to the temperature. It's still about the same temperature, summer or winter, but there is a big change in the insolation. So Titan's tilt, the Saturnian system is tilted a little more than the Earth-Moon system is. So we have the same kinds of seasons where in northern winter, like we're in right now, for Titan, the North Pole wouldn't be illuminated, just like it isn't illuminated right here on Earth, and the South Pole is illuminated all the time. But for Titan, these seasons take years, several years. And when we arrive at Titan with Dragonfly, and when Huygens arrived, and Cassini arrived, it was late southern summer, late northern winter, so kind of January-ish in Titan's year. Right. And so the sun was up all the time at the South Pole, and we saw clouds and even rain, evidence that it had rained on the surface around that time. But it takes a long time. It's years before kind of the weather patterns, which kind of follow where the subsolar point is, transition across the equator and up to the northern hemisphere. So when we arrive, we expect all of the clouds and weather to be at the South Pole. We wouldn't expect it to rain until probably 2040 or something like that, based on Cassini. But we're still tracking the weather. Cassini was wonderful because we got like a weather report on Titan, every few weeks. But we're still able to do that with other assets. And you're showing here the JWST observations a couple of years ago of some of these northern clouds, because it's just coming out of northern summer now on Titan. And then some follow-up observations by Keck, by the Keck telescope. So we're still tracking that, but the weather really does kind of track the sun, and so we don't expect to have too much in the way of weather. The wind speeds are a couple of meters per second, so again, much subdued compared to the kind of wind speeds we're used to here on Earth.
Gotcha. That's what you said. You don't expect rain till 2040. Like, can you imagine? Talk about a sluggish atmosphere. Like, around 2040 we might get some precipitation. We'll see. Yeah. I was hoping
we have to be robust, right? To that point, right? I mean, one of the things that Ralph has worked on is defining the environment, right? We can't always predict the weather, so we do have to make sure the lander is robust to be able to,
right. In case it gets an errant rainstorm.
Exactly, yeah.
Yeah, the lander does a wind check before it takes off,
right?
And will veto the flight if things are not looking right.
I was gonna say if you randomly get a shower, I guess you would just wait right until it passes over. You wouldn't try to fly on that or anything.
Exactly.
Yeah, it has its own
pre-flight checks that you do here on Earth.
Yep, like autonomous go-no-go poll that it does itself. It looks at all the conditions and sensors before it decides to take off, because it's not like, hey, here's the information, Earth, and then we're going to sit here for 70 to 90 minutes waiting for it to get to Earth. Is it round trip or is that one way?
That's one way.
That's one way.
That's one way. Yep.
So then you'd look at it and you'd say, it looks good to take off, and you send it back in the atmosphere sluggish, I guess, but that's still a few hours between it taking the measurement and it getting a response if Earth is controlling everything. So giving it the ability to do that sort of autonomously is how you have to set this up, right?
So we do exactly that sequence. So we'll get the data, and we will do a go-no-go here on Earth, but then Dragonfly is the final arbiter. So if for some reason something does change, it's again in Titan's day, it's not actually that much time. But if something does change in the conditions, then the sensors on board would report that, and the final go-no-go is actually made on Titan.
Yeah,
and our understanding of the conditions on Titan is not purely observational. We're not just limited by what Cassini and telescopes have told us. We have pretty good models now of the general circulation, not kind of like weather models, and they reproduce what we see. They show the same cloud patterns we've seen in the telescopes. Mm-hmm. They show the same dune orientations and patterns that we've mapped out, and those models predict that the rainy season at the equator won't be until years after the mission's nominal end, and they predict that wind speeds are of the order of a couple of miles an hour.
Yeah, I'm sitting here trying to think, have we ever sent a probe to another planet that was able to capture imagery of a raindrop or other world. Sorry, moon. It's larger than some things we call planets. But like, I don't actually know off the top of my head if that exists. But we're not going to get that till the 2040s, maybe.
So there is actually one image among 100 or so that the Huygens probe took on the surface of Titan.
Yeah.
It has a little blob that isn't in the other images.
Huh.
And the best interpretation is that it was a methane dewdrop that formed on the camera baffle and then fell off, right in front of the lens. And that methane was only there because the Huygens probe was warm and sort of sweated that methane vapor out of the ground. We have skids, and so we're well above the ground. That won't happen for us. But that really is the only equivalent. There have been some ice behaviors on Mars and maybe damp ground. You get into weird effects with salts, bringing the freezing point of water down, but not really drops of water.
Right, like little splashes in the sand or anything like to that level.
On Titan, it would be, of course, drops of methane.
Drops of methane, right. I have to get to that. I've seen a lot of people in chat talking about the methane. I've seen methane interact with a flare stack before on Earth. How do you have to design around that? Like, is the methane a hazard? Is it going to eat away seals? Is there any possibility?
Is it corrosive or anything like that?
It's actually a relatively inert material. I mean, in the absence of oxygen, there's no free oxygen on Titan, so it's not going to burn. This question came up, right? Engineers want to check everything.
You're not sending an ignition source to Titan, which is a perfect mix of methane and oxygen or anything.
Right, and you can imagine ignition sources, triboelectric charging or something like that, but there's no oxygen, so the stuff won't burn. We have done tests to make sure that the grease in the rotor motors doesn't dissolve away in liquid methane.
Right.
So there are materials compatibilities, but methane's actually a relatively benign material.
Gotcha. All right. Elysia.
That would make sense because, again, one of the recent stories that I remember reading about was on Mars, right? They just discovered that there are electric, sparks.
That was part of that work, yeah.
So if that were to happen on Titan, that would be really bad.
Yeah, so we actually picked that up on Mars with the Perseverance's microphone. It turned out it had a little susceptibility to electric signals as well. We detected the electrical signal and the sound. Now the Dragonfly actually has electric field sensors and it has microphones separately. So we'll be able to identify if there is blowing sand that becomes electrically charged.
Might we get any audio of flight on Titan, like the rotors going and the whoosh of the wind or something transmitted through the frame?
We have the technical capability to do that.
Yeah.
I mean, every bit of data we send from Titan is precious, but we have compression scheme to save data as much as we can. And sound is a very useful diagnostic tool of equipment health, right? If the pumps for the mass spectrometer are squealing, we'll know that and maybe can operate them differently. So I expect we'll have rotor sound at some point, I'm sure.
Yeah. I know it's not always the primary scientific objective, but when we get something back like that and it can be used for outreach or understanding or help people think that this is cool. It's like, here's the sounds of an octorotor flying on a planet. Like things like that really get people's attention. So it's a bonus to scientific payload, I guess, sometimes.
Yeah, that'd be really exciting.
Yeah. We always run out of time. Every single time we do one of these, we talk and talk and talk. There's so many good questions. There's so many good questions in chat. I've been trying to get as many of them as I can in, but there's no way we can ever catch them all. Is there anything about the mission that y'all think that we need to tell people that we haven't yet? We talked about so much stuff, but do we miss anything that y'all think is very important? Ralph, ZB?
I think we've covered a lot of ground. Nice. Yeah. I can't think of anything that we haven't touched on, at least. I mean, we could talk about Titan and Dragonfly for a lot longer, of course.
Like it's your job. We could talk like it's your job.
But no, we've I think we've covered it pretty well. Ralph, can you think of something we missed?
Nothing's coming to mind. Maybe we can talk about this for months. But let's note that we do have a dragonfly.jhupl.edu website where there's a lot of resources that people can learn more about the mission at.
I've got that. It's dragonfly.jhuapl.edu. And I am going to put that link into chat right now, as many chats as I can get to. If you click on that, you can get more information. I was reading about the mission before that. That's where I got nuclear-powered octocopter from, that I put in the title and stuff like that.
There's even an augmented reality model linked there that uses the CAD model. We actually use the augmented reality model as a design tool. To be able to kind of get one's head into the lander and see how you're going to work with things and how you're going to route the wiring and all of that. And there's a smaller version of that available on the website too.
Gotcha. What would I look for on the website to find that?
It's on the lower right. I think it can't remember what it says, but I believe it's on the lower right corner. Gotcha.
Experience Dragonfly. Explore and manipulate the Dragonfly rotorcraft landed on your computer screen.
Yep, that's it. And then if you do it on your phone, you can actually put it in the space with you.
Huh. You can see how big it is. It's like the size of a car.
See if it fits in your living room, right?
Not here in New York. Not in my living room.
All right, y'all, we have come to the end of our show today. Ralph, ZB, thank you so much for taking time out of your weekends here to tell us about the cool work that you're doing to send this massive rotorcraft all the way out to the moon of Saturn, Titan. So many good questions, so many good things that y'all are telling us about here. Chat was having a good old time. There's a lot of chat going back and forth, but just thank y'all so much for spending your weekend here with us.
Our pleasure.
Yeah.
Excellent.
Very fun talking with you.
Outstanding. Don't go anywhere. We want to say thank you after the show. But Elysia, we have some housekeeping for the next show, don't we?
Yeah. So, well, again, thank you both. This was amazing. For all of you tuning in, as you might recall, earlier this summer, we opened a brand new exhibit in our Space Shuttle Pavilion that explores another mysterious and unknown world of the depths of the ocean, called Mysteries from the Deep, Exploring Underwater Archaeology. And so if you're interested in checking it out, you still have one more month to come and see it if you're interested. It was co-produced by the Intrepid Museum and Flying Fish, and it explores all of the type of work and tools that people use to explore and recover things like ships and planes and fossils and underwater cities and things like that. So if you happen to be in the New York City area over the holidays, be sure to come by, check it out. It will be open through January 11th, and it is free with admission. And then next month, we will actually be on a short hiatus for Astro Live. But then the month after that, February, we'll be back with some live streams from our amazing annual Kids Week event.
Nice.
So by now, many of you who've tuned in are probably familiar with this. But if you aren't, it is our big week-long festival for kids of all ages during school midwinter break here in New York City. And we have everything from aerospace partners to Broadway shows. We have live animals and robots, and it's so much fun. Das and I typically do a walk around during one of the space days to introduce some of those amazing partners to you at home. And we also host our February Astro Live episode live from the stage there too. And so I can actually break this now. This is a breaking news, world premiere announcement here, a quick tease. We are super excited to be hosting NASA astronaut Jasmine Mogbelli to the ship.
Nice.
Who we actually, as you can see here, got to meet during our visit to the Neutral Buoyancy Lab a few months ago. So she's a U.S. Marine Corps test pilot. She was the commander of SpaceX Crew 7. She spent months on the International Space Station, got to do spacewalks. So we're super excited to be having her. She's actually from the New York area, too. So she's really excited to be coming to us. And we'll be talking to her about life in orbit and what's next. So yeah, come on by for Kids Week. That is the week of President's Day. Well, it'll be President's Day, actually, that week. So that Sunday is when we have our Astro Live. All
right. Well, folks, as always, we appreciate y'all hanging out with us. Remember, the shows don't just magically happen. They happen with that NASA Cooperative Agreement awarded to the New York Space Consortium, but they also happen because y'all show up, and when we do a show, you tell us how much you like it. So if this is something you thought was interesting, make sure you let us know down in the comments. I've seen a lot of great chat saying another fascinating episode here. One of the reasons we can keep doing this is because y'all think it's important. You think that it's valuable. It's something you're interested in. It's something you want to share with your friends and family because it's like, I didn't know they were doing that. So thank you so much for making it so we can keep these sorts of shows going and sharing the educational, cool space things with people out there over the internet. For now, that is going to be the end of our show today, and we will see y'all next time. Thank you so much for hanging out with us.
And here we go.
We have liftoff. Propulsion continues to be normal.
RCPA chamber pressure looks good.
Doubling up. Roger, with planet.
Water towers, fly! Yes! Tango down to nominal.
Fighting down to SC off. Bring in SC off. It's orange!
145. Oh my god! Oh my god!
Decollage. Look at that. Put that in the big bag, Segal.
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
This methane will be igniting in the flare, correct?
Yikes. You good? Sure. We don't need any more of these.